All right, guys, so today we are starting Chapter 6. Chapter 6 is the last chapter we're going to be covering this year. So for Algebra 2, this is the last chapter, and it's going to take us all the way to the final. So if you pay attention, I think we'll pick it up pretty easily. You'll understand it. If you don't pay attention, it will be harder than it needs to be. Now, what we're looking at is exponential functions and logarithmic functions. So the first thing we're going to look at, and what we're looking at today, are exponentials. Now, we consider a function to be exponential if it's growing from one value to the next more and more. Because when we talk about linear functions, say y equals x, well, as we plugged x and y value in, so when x was 0, y is 0. When x is 1, y is 1. 2, 2, 3, 3. And as we see, x increases by 1, the y values increase by 1. It's 1 to 1. Now, an exponential function, we can say y is equal to 5 to the x. And as we plug the x values in, 0, 1, 2, 3, 4, well, when x is 1, or when x is 0, y is 1. We plug it in, we get this here. When x is 1, y is 5. Well, we can see from 0 to 1, x increased by 1, but the y's values increased by 4. If we plug 2 into x, we get a y value of 25. Well, that's increased a lot faster because we've increased by 4. Now we've increased by 20. If we plug 3 in, we get 125. Well, we've now increased by 100. If we plug 4 in, we get 625. We've now increased by 500. And as we look at this here, the x value is increasing faster, or the y values are increasing faster and faster, even though the x values are only increasing by 1. Now, we can do this in a calculator. Clear this out. 5 to the x. And graph it, and we get this kind of graph here. Now, if I look at the table, guys, so when the y value, so when we plug the first one in, we got 1, 5, 25, 125, 625. At 5, we're at over 3,000. At 6, we're over 15,000. 7. By the time we get to 8, we're at 390,625. So just in the first 9 numbers, we've gotten over this here. Now, when we hit 9, it's actually gone over 1 million. So we see here the y values are increasing faster and faster. This is not something we've seen before because all the functions we've talked about so far have had a nice kind of increase to them. X squared did increase faster and faster, but we had to put a number in front of it to make it increase faster. Because even if we compare it to x squared, we get this here, and if we look at the table, well, 5 to the x gave us over 1 million at 9. With x squared, we're only at 81. It is increasing at an incredible pace. This is kind of why we call it exponential functions. Now, we have 2 types of exponential functions. We have exponential growth and exponential decay. Now, an exponential growth is a function, b to the x, where b is greater than 1. It is apparent for all exponential growth functions with base e. And we get this general shape here. Now, the domain, the values we can plug into it are anything. We can plug any value of x in, but it will not cross the x-axis. So just a number to an exponent, so a number to the exponent x, will not cross the x-axis. Because there's no way that we could put a number, 5, to any power and get 0. Just doesn't work. Any questions on this here? So exponential growth if the base is greater than 1. Now, it's exponential decay if the base is between 0 and 1. And this is the parent graph for this here. Now, again, it will not cross the x-axis for this here. And the range is greater than 0. Now, we can get it to cross the x-axis, but to do that, we have to subtract a number from it. Because if we look back at our graph here, well, let's remove the x squared. We can see here, it looks like it does intersect the x-axis, but it actually does not cross it. The only way to get it to cross it is, we'll do this one here in red, 5 to the x minus 3. I'm going to subtract 3 from it. Okay, now it does cross the x-axis, but we moved it down 3. So what it's telling us now is that it does cross the x-axis, but now it does not cross the line y equals -3. Now it doesn't cross that line there. There is a line that it will never cross somewhere, and it's just going to move according to the graph. Now, for all the ones we'll look at, we're just going to look at b to the x, a number to the x. We're not going to look at it moving up, down at this point here. So, are you ready for the first example? We ready for this? Okay. First thing, tell whether each function is an exponential growth or decay. Then, evaluate for when x is 2. So the first one we're looking at, y equals 2 to the x. Is this a growth or decay? You will for the homework, yes. Can we say this is a growth or decay function? Is the base greater than 1 or between 0 and 1? It is greater than 1, yes? Because the base is what? 2. So if it is between 0 and 1, it is what? If it's greater than 1, it is? So this here would be exponential growth. Half of it, and then we need to evaluate it when x is 2. So we're saying y is equal to the second power. Well, what is 2 squared? So we put 2 in for x, which ended up squaring it, and that's it. Now we could have done this in the calculator. We can say 2 to the second power, which is 4. That's it. Now let's look at the next one. Y equals 1/2 to the x. Decay, because we have a fraction, it's less than 1, so this is decay. So we replace x with 2 because we're evaluating it for 2. So 1/2 squared, which is indeed 1/4. Any questions on A and B? Let's look at number 1. So we have y equals 1.3 to the x. Since it's a decimal, this would be growth. Well, if it's bigger than 1. So 0.5 would be decay because it's less than 1 but greater than 0. Here it's greater than 1, so it would be growth. Now 1.3 squared. Now unlike the first two we did that are kind of easier to see, 2 times 2 is 4. 1/2 times 1/2 is 1/4. 1.3 times 1.3 is, well, it might be easier to just type this one in, is 1.69. Now let's look at the last one. Y is equal to 1/3 to the x. This would be decay because 1/3 is less than 1 but greater than 0, so it is decay. And if we do y equals 1/3 squared, we would get 1/9. Questions on this here? Right, we're doing 1 times 1 and 3 times 3. 1/3 times 1/3 gives us 1/9. Now, any questions on any of this here? Now, notice that we did say the base has to either be greater than 1 or between 0 and 1. So when we talk about any of these here, these functions, these exponential growth function, guys, or exponential decay, we are not talking about negatives. Because when we looked at 5 to the x, I'm going to put it back here, we got this graph here. We've seen how this looks. Now say, guys, we took parentheses negative 5 to the x. What kind of graph do you think we would get? Probably still growth. Now, we haven't looked at what decay is, so I'm going to turn this one off for now. Let's change the color of this back to what it was before. And then let's say alpha y equals enter 1 over 5 parentheses to the x. So this one here is decrow. So the blue one is decrow. The blue one is growth. The x and the black one is decay. So the blue one is exponential growth. The black one is exponential decay. And as we go from left to right, the blue one increases. The black one decreases. It goes closer to x. The blue one goes farther away. So as we look at both of these here, what do we think this one's going to do? We ready to see? So let's look at the table and see what the values do. So for the one in red, negative 5 to the x, well, at 0 it is positive 1, yes? But at 1 it is negative 5. At 2, it's positive 25. At 3, it is negative. So it's flipping between positive and negative values. We don't have a graph because it's not a function because it doesn't have a smooth curve. It's not considered continuous. Because a continuous function has a nice smooth curve to it. It doesn't jump from these positive to negative values. So we can't really consider negative 5 to the x as an exponential growth or decay function because it does this jumping motion. And that's why we really don't talk about having a base, this 2 or 1.3, being negative, because they don't work. Now there's another one we don't talk about or don't really work with. And that is if, well, the base is 1. Because what's 1 to any power? 1. So it's just a straight line at 1. It's not going to do anything. Number 1, guys, would be, how about number 2? 2/3 would be decay because it's less than 1. 0.25 to the x is, and 1.5 would be. Any questions on any of this here? We have now officially finished 6.1.
What? We're done?
Now we're going to look at 6.2.
Oh, wait. So, do we have any homework?
Yes. Now, the other part of this lesson, the natural base E. The natural base E. Now, the history of math is marked by the discovery of special numbers, such as pi and I. We know pi is an irrational number, a non-repeating, non-terminating decimal, 3.14, and continuing on. I, we know, is the square root of -1. It's an imaginary number. Now, E is another special number. It's called the natural base E and is represented by this expression as x approaches infinity. So 1 plus 1 over x to the x. And if we add all these values together, we will get closer to E. Now, we will never get to E because E, just like pi, is an irrational number, a non-repeating, non-terminating decimal. And if we wanted to calculate it out, what we'd be doing is 1 plus 1 over 1 to the x. And we'll add 2, well, 1 over 1 to the 1. We'll add to it 1 plus 1 over 2 squared plus 1 over 3 cubed. Well, we keep all these here, well, not adding, but each of these values here, as we increase going along this line, we will get closer and closer to what the value of E is. and it'll approach this here, 2.71828182846 going on. Non-repeating, non-terminating decimal is E. Now, E does work like a variable in most cases. So, e to the third times e to the sixth, whenever we multiply like bases, we add the exponents. E to the sixth times e to the third. If we multiply like bases, we add the exponents. So 3 plus 6 is? That's it. Because when we multiply like bases, we add the exponents. When we look at this one here, 16 divided by 4 is? Now, when we divide like bases, we don't add. We subtract the exponents. So 5 minus 4 is 1. So it'd be e. If we wanted to type this into a calculator, we would have to do 4e to the first. Calculator needs an exponent for e. No matter what it is, even if it's 1, it needs an exponent for it. Now, for us here, we're not finding the value of these. We just want it as 4e would work. 4e to the first would also work. Questions on any of those here? Now, the next one, we would apply this square to both, which would give us 3 squared. And 3 squared is 9. 3 times 3 is 9. Now, our properties of exponents, an exponent to a power, powers of powers, multiply. So negative 4 times 2 is negative 8 x. So the power of 2, we're squaring it, guys. So we're squaring it. So 3 squared is 9. Now our e to the negative 4x squared, powers of powers multiply. So our negative 4x times 2 would give us negative 8x. But to make that exponent positive, we have to move it from the numerator to denominator, from the top of the fraction to the bottom. Gives us 9 over e to the 8x. So to make that exponent positive, we just moved it from the top of the fraction to the bottom. Questions on this here? Any questions on A, B, or C before we look at 1, 2, and 3? Yes, e to the 7th times e to the 4th. Since they are like bases, we would add the exponents. So 7 plus 4 would indeed be 11. Now the next one, 24 divided by 8 is 3. Then we'd have e. 8 minus 5 is 3. Now the last one here, we do need to apply the power of 3 to both. So we'd have 10 to the third. And 10 to the third is 1,000.
Oh, yeah, that's right.
E. Because negative 3x, we would multiply it by 3 and give us negative 9x. Now to make that exponent positive, we would move it from the top of the fraction to the bottom. Any questions on these here? Let's look at one more. Let's say the cubed root of 1,000e to the 9x. So it's a little bit like the last one we did, but instead of applying a power of 3, we're going to apply a cubed root. Now it is a little bit different because if you notice the 9x is not negative, I made it positive just so it works a little bit nicer. Now, the cubed root of 1,000, guys. Oh, 10 to the third was what? Was 1,000, yes? So we could do it in a calculator. We can say 3 cubed root of 1,000 is 10. 10, yes. So we can say 10, because we can take the cubed root of 1,000 in the calculator. Nice, it'll do it for us. For e, we can really look back to our previous chapter. N is equal to, the nth root of a to the x is equal to a to the x over n. And if we apply it to e, we'd have e, well, the number on top of the fraction would indeed be 9x. The number on bottom, our root is 3. Well, what is 9x divided by 3? Because 9 divided by 3 is 3, and then we would have x. So the cubed root of 1,000 e to the 9x is 10e to the 3x. And that's it. Are you ready for the hard part? Yes?
Oh, there's a hard no.
The natural base e function. When a, the number in front of e, is greater than 0, and the number in front of x in the exponent is greater than 0, then it is exponential growth. When the number in front, guys, when the number in front of e is greater than 0, and the number with x in the exponent is less than 0, it is decay. So when we're talking about the number in the exponent, r is greater than 0, we're talking about the exponent being positive, because numbers greater than 0 are positive. If the number in front of the x in the exponent is less than 0, it means it is negative. So if the number in the exponent is positive, it is growth. If the number in the exponent is negative, it is decay. And this is still following the same property we started the chapter with. As if we said the base is greater than 1, it is growth. If the base is between 0 and 1, it is decay. Now, E is defined to be 2.718 continuing on. So Y equals E to the X. X is positive, so it would be growth by this here. Now, also, E is 2.718, yes? Is 2.718 greater than 1? So no matter what we put in the X, if it's positive, it would still be, have a base greater than 1, it would still be growth. Now, if we said E to the negative X, by this definition here, it would be decay, yes? Now, to make the exponent positive, we would rewrite it as 1 over e to the x. And by the properties of exponents, we can apply this here. We can pull the x out. And part of the reason we can do this is because, well, just applying x to e would give us e to the x still. 1 to the x, well, 1 to any power is still 1, so I can pull that x out. But what this is telling me is that I have 1 over 2.718, this number here to the x. Is that fraction between 0 and 1? Yes, because 1, the number on bottom is bigger, so it's still between 0 and 1, yes? So by the definition we have to start, is this here, guys, between 0 and 1? So it would be considered decay. Now, when we don't have to go through this process here every time we get a negative. We just know if the base is e and the exponent's negative, it would be decay. So looking at this here, 3e to the x, would this be growth or decay? Because the exponent is greater than 0. It's positive. How about b? Decay. The exponent's less than 0, it is negative. How about number 4? This would be, because the 1/2 doesn't matter. It's not affecting the growth or decay. It is the exponent, if it's positive or negative. Because it's going to increase slower than just e to the x because of the 1/2, but it's not changing it from growth to decay, or decay to growth. Now number 5, 4e to the negative x would be decay, because the exponent is negative. And last one we would have questions on any of this here? And that's it.